Dang, I got stuck with an add. Okay, so we can have a function. It's 8x cubed plus 72x squared plus 192x. We want to find the first derivative. This one we can do just using power law, or power rule, right? That should be straightforward. 8 times 3 is 24. So 24x squared. What's 72 times 2? I'm going to have to bust out the old calculator for that. 72 times 2 is 144. So 100 and... Shake. What the fuck? No! Oh no, which exam is it? No, not like this. Will I pass my proof with flying colors? No. Damn you, 8-ball. Okay. That's not super obvious, so we might want to double check that. So let's just verify that. So we have 24 times negative...
Is that a philosophical? The point is a fundamental concept, infinitely small yet critical in geometry. It's sharp enough to cut through the zeta nonsense. What else you got?
Okay, so it is true. It is true that g prime at -2 is 0. Now, we want to know whether there is a local min or a local max at -2, so we're going to use what's called the second derivative test. So to use the second derivative test, we take the derivative of the first derivative. So 24 times 2 is 48. So that's going to be x plus 144. And we want to evaluate the second derivative at 2. And this hopefully should give us some information about concavity, right? So let's throw -2 in here. We'll add our 144. That should give us 48. Really? That seems so bizarre. I guess 144 must be some multiple of 48. It must be 3 times 48. 3 times 48. Yeah, that's so weird. Okay, so g prime at -2 is 48. Based on the sign of this number, this means concave up, right? So concave up. So we're basically looking at a point where we have a minimum. So at x, you can look at the graph is concave up. Does this mean there's a local minimum or local max? There's got to be a local minimum at -2, because that's going to be our lowest point in that particular neighborhood. The function has one local minimum and one local maximum. This function has a local minimum at x equals blah with a value of blah and a local maximum. So we need to find these things. We can find candidates for local maxes and local mins by setting the derivative equal to 0. So our derivative is 2 times 3, which is 6, x squared. 36 times 2 is 72, x plus 210. Let's set our derivative equal to 0 and try to find all x values that satisfy this quadratic equation. We could try to use the quadratic formula. That seems like a pretty reasonable thing to do. I'm going to maybe show how to factor this, but you can also solve this with the calculator. You can go into your equation solver mode and go into the quadratic equation, and then just kind of input all of the coefficients of the x's. So if you have a graphing calculator that'll do that for you, it kind of gives you what those two solutions are. So 7 and 5 should be the solutions that we're looking for. So let's see if we can show that algebraically. I could probably divide everything by 6. So I think 72 divided by 6 is 12. 210 divided by 6. I don't know what that is, though. 210 over 6? is 35. Okay, so that makes sense why we're getting 7s and 5s. And then if we want to factor this, the 7 and the 5 become a little bit more clear here in the factorization process. So 5 and 7 are going to be the particular places where we could have maxes and mins. So sometimes these are called critical points. And once you have an idea of what the second derivative test or maybe the first derivative test does for you, then you can get a little bit better sense of what these are doing. Because right now, is there an easy way for us to kind of figure this out? I guess maybe we could use the fact that this is a cubic, and a cubic would look like this for a is bigger than 0. So we can probably reasonably conclude this is going to be our max, and probably reasonably conclude that this is going to be our min. But if you're unsure, and you don't really know what a generalized cubic looks like, you can take the derivative of the derivative, and that's going to give us some information about concavity. So if we go ahead and take the derivative of our derivative, 6 times 2 is 12, and then we get a minus 72. And then we're going to sub both of these x values into our second derivative. And we should get information now about what's going on. So all we really care about is the sign, but let's go ahead and just evaluate these anyway. So at 5, we have 12. So 12 times 5 takes 72. That's going to be a negative number, right? So negative 12. Not negative 7, negative pen, please. Negative 12, and then I think if we put 7 in, that should be positive. So that will be positive 12. So that means we can make some conclusions now about what's happening at 5 and at 7. So at x equals 5, we are concave down. So x equals 5 is a max. And at x equals 7, we're going to be concave up. So x equals 7 is a min. So that's nice. We have that information now. So let's see if we can fill some of this information in up here. So the function has a local minimum at x equals 7. X equals 7. And a local maximum when x is equal to 5. And if we want to figure out what the values are, we just are going to go ahead and make a substitution of that x value back into the original function. So my original function is 2 times 7 cubed. Boop, boop, boop. Minus 36 times 7 squared. Plus 210 times 7 plus 5. So the value at 7, this should be the minimum value, which is kind of crazy. So the minimum value should be 397. That's weird. That doesn't feel like a minimum, but let's see what happens at 5. So at 5, we have that, and that, 210 times 5. So 405. Okay, so yeah, our maximum happens at 405. So not a lot of difference there between our min and max. So it must be like quite a huge, like steep increase, and maybe like in the middle, it's not really doing too much in the middle, but enough that we can find a max and a min. Now, question 3 looks like it's kind of interesting because we have some boundary values, and boundary values can mess up our analysis a little bit. So these boundary values here are going to make this more interesting than what it normally would be. So if I want to find the highest y value and the lowest y value possible on this interval, those things could technically happen on the boundary value. Because we're kind of restricting our viewing window for x's, and so that means that the y's can get a little bit restricted as well. So let's actually look at this. 5 take 7x squared. So 5 take 7x squared. But we want to view this. So this clearly has a maximum at 0. And that's it. But we're restricting this to, and we're only looking between -5 and 1. So I only want to look at this between -5 and 1. So here is, geez, that is really far down. So I'll try to adjust the axes a little bit so you can kind of see what the shape of this function looks like. So here it is, between -5 and +1. So I still think that the maximum is going to happen at 0. The maximum is still going to be 5. But it just so happens that our minimum, our lowest y value, happens at the endpoint of -5. So these particular endpoints, in this case -5 and +1, they could theoretically be a y value where I hit my max or hit my min. This only happens when we're in a restricted viewing window, though. So generally, the procedure to work through a question like this is to find the derivative. In our case, it's going to be -14x, and we're going to set that equal to 0. And we can solve this to get x is equal to 0. So we call this a critical value. And any of these x values that we get here are potential values where we could have a max or a min. Now, we just saw on Desmos that the max or min could theoretically happen at an endpoint. So whenever we have these boundary values, the last thing that we want to do is just kind of evaluate our original function at the critical values and evaluate our original function at the boundary numbers as well. And if I can find these 3 particular values, then I can kind of sort through these values and figure out which one's the max, which one's the min on the particular viewing window that we're looking at. So are any of these easy to do? I guess at 0, we're going to get 5. At 1, we're going to get 5 take away 7, which is -2. And then at -5, we're going to get 5 take away 7 times 25. So 5 take 7 times 25. So that's going to clearly be our absolute minimum, because that's our smallest y output. So the absolute maximum value is 5. Right, so the maximum or minimum values represent the y numbers that we're working with. So the max value is 5. This occurs at x equals 0. And then the min value is going to happen at -170. And that's when x is equal to -5. So that's what we're looking for there. So again, it looks like we here have a polynomial function with a viewing window of -12 to +5. So we have the absolute min. Wait, the absolute min is at, and the absolute minimum of f is blah. Okay, so we need to find the x and the y values for the absolute min and absolute max. Okay, this is a bit more interesting because this is now a cubic function. And this cubic function usually has more critical values for us to work with. So it's still kind of the same procedure. We're going to take f prime. We're going to set that equal to 0 and see if we can figure out where that quadratic is going to have some zeros. And then that should give us places where we might be able to see maxes and mins in our original function. So 2 times 3 is 6. And that's going to be x squared. We'll bring our 2 down, so 12 times 2, so 24x minus 192. And let's set that equal to 0 and see if we can factor this and find some values of x that might give us 0 here. So if we divide by 6, I think everything here is divisible by 6. So x squared plus 4x. I don't know what 192 divided by 6 is, but I feel like that should theoretically be possible. Sorry, 192 divided by 6. It is 32. So now I'm wondering, is it possible to easily factor this? Why do 8 and 4 feel like a thing? Maybe like positive 8 and negative 4. So x equals negative 8 or x equals 4. Those seem like reasonable x values to think about. So remember, our goal here is to think about all of the x values in between negative 12 and positive 5. So our critical numbers of negative 8 and 4 do fall in that interval, so that's good. We don't have to exclude anything. So now it's really just a matter of evaluating our function at some different points. So we can evaluate our function at negative 12. We can evaluate our function at positive 5. That's going to take care of the boundary values. Then we need to evaluate our function at the two critical numbers as well. And so doing that and kind of analyzing what these y outputs are should allow us, I think, to kind of finish off this question. So let's pop up our calculator. Let's start programming some of these values in for our functions. Let's go 2 times, let's start with our negative 12. So negative 12 cubed. It's going to be click SMR here for a second. So 12 times, we'll do negative 12 squared minus 192 times negative 12. And then we'll add 8. So I get as a y output 584. That's pretty big. So 584. And now that we have everything programmed in, we can just go back and basically we'll delete all the negative 12s. We'll pop in the next number that we need, which is 5, let's say. So 5. We'll pop in 5. Pop in 5. And then there we go. So at 5, we should get negative 402. These seem like crazy fluctuations. And then we just kind of rinse, lather, repeat. So let's go ahead and we'll delete this. We'll pop in our negative 8. Again, we'll get rid of 5 here. We'll pop in negative 8. That looks like that's the biggest y value output so far. So 1288, so 1288. The last one we need to check is what's happening at 4. Because that could be a potential absolute max or absolute min. Boop, boop. And so we get negative 440. Hi, Sereno. How are you doing? Nice math for us, the mortal people. Yes, yes. Basic introductory calculus is always nice math to do, right? So what's the biggest and what's the smallest y value that we get? It looks like the biggest y value happens here. And it looks like the smallest y value happens here. So our absolute maximum happens at 1288. That's when x is equal to negative 8. And the smallest y value output we get is negative 440. And that looks like it happens when x is 4.